Okay. Good afternoon, everyone. I'm Sanjib Kumar from Texas A&M Corpus Christi, and I will be talking about detecting data leaks in multi-user LLM applications using automated user-scoped taint analysis. So let's start with a story. So start with a story with OpenWebUI. So OpenWebUI is one of the most popular front-end applications for serving LLM applications in, like, it's a current trend to serve LLM applications in many of the enterprise platforms. So you can already see the statistics here. It already has been downloaded almost 300 million times. There are more than 430,000 community members actively working with the OpenWebUI, and the GitHub stars are rapidly growing day by day. It's already been 142,000 times. And not only that, Texas A&M University system also creating a AI framework that will be used by students, faculties, and even staff members for any AI tool uses, and so they can chat with the AI instead of using ChatGPT, Claude. They can use our own, like their own UI framework, like LLM framework with the Taint AI framework. So in that case, we also see that they are using OpenWebUI. Basically, a fork of OpenWebUI has been used in this Taint AI framework. So all of the students, faculties, and staffs from all of the universities that's operating under this Texas A&M University system has been using this. So yeah, it's a pretty huge project for LLM applications. So in the OpenWebUI, the story starts here actually. So in the OpenWebUI, we have found a major bug that is responsible for like leaking one user's data to another user's chat in a multi-user environment. So what happens is here, as you can see, that when a team shared a single OpenWebUI instance, they have the same backend for the OpenWebUI. That means they share the same Chroma vector database for vector embeddings. They share the same SQLite database for conversations storage and many other things. And also they use the same LLM API call and API request handler for the same team. So even though can be different users, but the backend is same for everyone. So what happens is here is that in those bug, we have seen that in terms of 2 or more cases. So for example, if user A uploads a PDF through the chat interface with the OpenWebUI front-end, what we see that the PDF gets chunked and then embedded and stored in the vector database, so that user A can query that later. And in the meantime, if user B also uploads another PDF with their own front end, the PDF goes to the same vector database after embeddings and things like that. But the problem is there, we have seen in these cases is that if the PDF of user B is empty, so there is no content in the PDF, then what happens is, although the conversation gets stored in the SQLite database, the actual chunks does not get stored in the vector DB, because there is no chunk to embed or no chunk to actually store in the vector database. So what happens is, after user B uploads their PDF, empty PDF basically to the chat interface, and then ask some questions, for example, get me a summary of the PDF. So what happens is, the request go through the vector database. It does not get actually anything from the PDF of the user B. So what it does is, it gets the top candidate chunks, and it actually includes the data of the user A. So what happens is that it gets the data of user A, then it creates a prompt to send to the LLM model with the embeddings, and LLM model return a response that can be forwarded to user B. So basically user B gets the response for user A, which is not supposed to happen, and this is a huge data risk. And we are seeing these cases not only in Open Web UI, but also in many other LLM applications. So in one of our another research based on LLM security, we have found out that around 42% of popular open source LLM powered applications support multi-user mode or in local or cloud deployment. And what we have seen is that in those LLM powered apps, while developers are creating those applications, they build those for one user or single client environment. They actually have not kept in mind that it can be used in a shared cloud environment or a deployed it can be deployed as a team environment or in an enterprise platform. So these bugs occur later on, not in the first time, and we have also seen that in many cases the resources are shared by the users. So for example, the caches, the databases, and the LLM API calls are mostly shared in this application. So this is a problem we are finding in the LLM industry right now. So you may ask, okay, so there is like taint analysis, there is already some taint analysis there. So we have Flow-Droid, Clank static analyzer, P-taint, and also there is a dynamic analyzer here, which is libdft. So we already have that, but there are we have found some limitations on those static analyzers. And for example, we have seen that none of these taint analysis tools support automatic source and user input source and output syncing. You have to basically, a human have to tag those inputs manually by in hand, and then it gets source. And also we have seen that they do not support multi-user environment. They do not have support for access control or permission level policies. So there is that, and as libdft works on dynamic environment, there is a performance overhead on this, and there is also a LLM black box in here. So what is LLM black box? Basically, LLM is kind of a new thing in 2000, which came after 2023, and we have previous taint analysis tools have not considered LLM analysis as a critical functions, calls, or anything like that, because when you call an LLM API, so for example, if the client is using light LLM proxy, you don't know actually what happens on the server here. You don't realize that it can be vulnerable. What you get, you don't have idea of this like LLM API calls, like what's happening inside. So we consider this as a black box, and we also trying to solve this LLM black box situation here. None of these existing tools consider LLM black box as a critical thing, because on that time none of this LLM was not a thing. So to solve these problems, we find out two ways how we can identify the issues and solve this issue. So first of all, we tax each user's input with like permissions as well as tags. So there will be origin tags for all of the inputs of the users, and then we use a static analysis with those tags, and we will track those tags throughout the program, that if the tags has been reached by two or multiple users. So if one tag is reached by like multiple users, we can say that there may be a data scope overlap, or this thing should not happen. So we built a framework based on that. So we call it access flow graph. basically we also have, we named these two stages. One is multi-user, multi-permission, and basically when a user provide some input, and also they have some permission, so we call it multi-user, multi-permission. And when we propagates through all of this, propagates the text through all of this like program, and the whole program, we basically check that if it has been reached by other users or not, and we call this part scope taint pointer analysis. In short, it is STPA. So here is like the first part, what does MUMP or multi-user, multi-permission do? So we already created a database or data set of like popular function signatures from popular LLM API SDKs. So there is OpenAI, Anthropic, and also Gemini. So we have this database of all of these popular LLM APIs, and we keep the function signatures here. And then in the program, we match those function signatures to our data set and check, okay, so if these calls are being called as a LLM API call or not. So if we find that this is a LLM API call or something we need to take care of, so for example, it is using like shared Redis environment, shared database, something like that, we can identify those functions using the function signatures here, and we also tag each user's input by their permissions and access levels. So this is the first part where we are basically tainting all of the user inputs and permissions here. Then in the second part, that is a scope taint pointer analysis. So just like I said, we built a pointer assignment graph of the whole program, and we already have the text from the user's input from the first stage, which is MUMP. So then we propagate the text along the whole pointer analysis graph until there is no change in the program. Then we flag any abstraction that any text that reaches 2 or more users, which is not supposed to happen. So for example, there is actually an example. If we go to the next slide, so you can see here, this is a simple example of how data leaks happen in multi-user environment. So for example, here there is 2 users calling an LLM API. There is also a cached database using Redis, where the questions and answers are being cached, because like we don't have to call LLM API multiple times. If the questions is already asked, we can get it from the cache. But this environment is like prone to have like the data leak in here, because in this example you can see here, as both of the users using the same Redis endpoint for the same Redis database and as a cache. So when the user asks a question, you can see here in line 12 the cache key that is like helpful for like setting the cache and getting the cache. The cache key does not have the user identification, so there is no filtering for users in the cache key to get or to set. So only the questions is being used as the cache key here. So there can be a problem that if the user asks like, what's my first event today? So at the first time, the program will say, okay, so this question has not been asked anywhere else, so let's get the answer from the LLM. It gets the answer, then it sets the cache in the Redis database. But when the user 2 asks the same question, as there is no user filtrations in there, so they get actually the same answer in here, because it's coming from the cache database, and in the cache key there is no user filtration. So that's a big problem. So how we can solve that using AFG? So that's how we will be talking about in this stage. So at first step, we will do multi-user, multi-permission stuff. So in here you see that users A questions are being tagged as O1, user B's questions are being tagged as O2, and also user A's identification and permissions will be saved as O3 and O4 in here. So this is the map stress, pretty simple here. There is nothing to do. Then in the STPA stress, although I might say that in the MAMP stress there is another thing we need to do. So for example, in the line 10 you see that we have client get connection that is basically connecting to the same Redis Redis cache database here. So that's also something we need to taint, because it's in the shared environment and this is a shared object. So that will be tainted as O5 tag, origin tag, and then there will be some other tags. So for example, the questions will be tagged as O6, the answers will be tagged as O6, and questions are already tagged in as we have seen in the previous slide, that it's O1 and O2. So O6 is the answer in here, and O5 is the Redis connection that we are tracking right now. So in the STPA part, what we do is after we create the after we create everything, so we go through each of the lines and get track where the tag has been raised, and we find out that the tag has been raised in user B as well as user A, which is O5. So this this should not happen at all. So we flag that as a scope overlap, data overlap, and by that we get the data leaks. So we also built a prototype for this AFG program, and the prototype we have found that it can actually get 3 positive outcome and 0 false positives in this prototype. And the prototype is available in the GitHub, and also this is the summary. As we already seen, we are trying to solve LPAs that leaks one user data, and our MAMP and STPA basically tags those taints automatically and also find out where is the data scope overlap. So there is also a future work. We will try to run this in a dynamic environment using MATSIM, which is a deterministic simulator, and we will make sure that the leaks are confirmed and also try to give the developers a reproducible environment. So okay, so that's it. Our FG can do all of these things that other existing tool cannot do. So yeah, so okay.
Thank you. We can take one quick question.
Hey, thanks. Great presentation. So one question was around you are mapping LLM API function signatures, right?
Yeah.
To identify that this call came from a user A's LLM versus user B's LLM. Can you briefly explain how you're doing that?
Yeah, so basically, so for example, if you go to like the OpenAI SDK in Rust, their GitHub repository, you will see that OpenAI SDKs will be called using these functions. So in these functions, there will be, the function name will be as OpenAI chat create, or chat completions, and there will be parameters type, and there will be return type. So these function signatures are similar across like all of the LLM API calls in that specific language, like for example Rust, in that specific like LLM provider. So for example OpenAI, this for OpenAI's case, this will be standard across all of the Rust examples. For Python, there will also be function signatures for OpenAI. For Gemini, there will be other type of function signatures. So we have a data set of those function signatures, and we basically try to find out the function signatures in the program's code. So if we find out, okay, the signatures are matching with one of the OpenAI API's calls or Gemini's API call, then we can identify, okay, this is a LLM API call, and yeah, we need to we need to work on that.
I see, but you're not using that to distinguish between users. It's just okay. Thanks.
Okay, so let's thank our last speaker for today. And give